Okay, so formally I welcome Professor Y.N. Mohapatra for this talk, and on behalf of the physics department, we are grateful to you that you accepted our invitation. So,
Immediately.
yeah, so this time we are organizing BITS Alumni Colloquium series. So you are the third person who is delivering the talk. The first talk was delivered by your friend Professor Patrick Das Gupta.
Okay.
And the second was relatively young BITS alumnus, Dr. Prahar Mitra, and the third one is yourself.
Okay.
So, as there is no further requirement for your introduction to BITS Filani, because you
Absolutely.
are BITS alumnus and you are familiar with the BITS system. So, I welcome on behalf of the physics department. And now floor is yours. So, I
Yes.
invite you.
Okay. So can you see my presentation already?
Yes, yes.
Okay. All right. So thank you. As soon as your invitation came, I immediately agreed because it's my alma mater. All right. So today I'll talk about flexible soft and soft electronics. I have kept deliberately the presentation at the level of undergraduate level, thinking that there'll be a lot of students from our physics or electrical engineering here. All right, so I'll keep it at that level, and I'll take my examples. So I am, of course, from physics here, material science program, and National Center for Flexible Electronics, and Samtel Center for Display Technologies. All right, so of course, I'm proud to be a Bitsian. Okay, it's a multidisciplinary foundation has given us a solid start to our career. We had a large number of career-inspiring teachers, and of course, luminous and stellar array of peers. Okay, and I'll specifically mention Professor. At that time, he was the Dean of Research and Research also, Professor Vinod K. Tiwari, who had a hand in shaping our future career in physics. He was an extremely inspiring teacher, and it's because of him that I am today a condensed matter physicist, and otherwise, maybe I would be a particle physicist. All right. Okay. Above all, okay, it's an emotional connect with those formative years in a magical place. We used to call it Oasis. All right. So let me say that over the next 30 or 40 minutes, I would say why flexible or soft electronics, a little bit of introduction to worldwide efforts, and I will take up some key problems to give you an introduction of physics-induced technologies, specifically materials, inks, and substrates, and examples of fundamental problems, and a little bit of technology-induced large area printing. And I will introduce you to current challenges. Okay, and it will be pitched at the sort of UG level physics. So let me give you a history that I have been a normal semiconductor physicist, but since 2000, this is already 20 years, I have been into this topic of flexible electronics or organic electronics. In 2000, we established here something called Samtel Center for Display Technologies, which was primarily organic electronics. Okay, and then we went on to make the first passive matrix display meeting industry standards. So I am here a physicist, but an applied physicist. Okay, unlike Patrick, who is a theoretical physicist that you had heard him. All right. So applied physicists, of course, it was with physics. We normally take up questions of electrical engineering, which only physicists can solve. Okay, a physics background is required. So it is in that spirit that we do this, which must meet also industry standards. In 2007, actually, I led a group to country's first major program on what is called the printable electronics. And then, of course, we started off many technology programs. And 2014, which is 7 years back, we started the National Center for Flexible Electronics, a key center for flexible electronics in the country. So that is, so you are welcome to visit us, okay, for a project or just visit us. So, and this is with generous help from the Ministry of Information Technology and of course IIT Kanpur. So what is this technology platform? These are physics induced. I'll keep on telling you what is the kind of physics that went into this technology platform. This technology platform is system on plastic or paper. Okay, that is everything that you make is on a plastic. So for example, here you can see it is photovoltaic or battery source. You'll have sensors, you'll have electronics, which means TFT, memory, diodes and passives, and actuators, LEDs, displays and speakers, all integrated into a plastic or paper, okay, for universal use. I hope you can see my cursor. Yeah, okay.
Yes, yes.
Yeah, okay. So just to see that we have for each of these technology development, we have a group. This you may not read all that, but majorly we make thin film transistors, organic light emitting diodes, organic photovoltaics, all kinds of sensors, even biosensors. We make functional inks and printed batteries. So with once you have capabilities of these, okay, you can now go to technology integration and make memory and logic circuits, solar modules. We have a major program on anti-counterfeiting, healthcare devices, displays, and smart packaging. So these are technology integration programs because we have our core technologies on some of these things. All right. Uh, so of course we know diodes and transistors are part of electronics. So I call diode as the wheel of electronic civilization. All right, and transistors is the three-legged, okay, brain behind the electronics. So electronics needs both, okay, and the idea of electronics is of course integrating large scale, and so integrating on large scale on plastic is what of course it has been achieved in microelectronics, but in this case, so let me ask you, what do you find common to all this? This is, you can see a diamond, the flowers, and graphite. Okay, I'm sure you can make out what is common is carbon. All right. So and so carbon can so if it is crystallized, it is diamond, and it gives you organic molecules. Okay, of you already know about the C60 and or carbon nanotube, and of course graphite, and which is now giving rise to a major revolution in graphene-based electronics. So what is common to is carbon. So we would in future, we are certain that we are moving away from silicon to carbon for many applications. It's not that we are going to do away with silicon, but there'll be a lot more applications with carbon as the basis. So silicon was the hero of the microelectronics revolution, and carbon is going to be the hero of the macroelectronics revolution. That is what I'm going to talk about today. So is not carbon or silicon, but both carbon and silicon. Silicon for microelectronics, carbon for macroelectronics. Okay, so this is a science-induced technology, and if I want to say, it's of course the Heeger and McDermott and Sirikawa. Sirikawa was a physicist, a chemist, and Heeger and McDermott were physicists, and they got the Nobel Prize in 2000 for making plastic conducting. Okay, and in the same year, the physics Nobel went to heterostructures and IC, Alfarov and Kromov for heterostructures and Kilby for integration. So these two ideas were actually used by two more physicists, okay, Chang, who was in Kodak at that time, now of course is an academician. He discovered the small molecule organic light emitting diodes in 1986, and now Sir Richard Friend, which also did that in polymer in 1990. So these are new physicists who are adept at both being academicians and startup industries. Okay, so this is a beginning. So in the heart of this technology is something that you can see that this benzene rings. So this is what you are seeing is ALQ3. Okay, that is aluminum at the center, and benzene rings in a particular format. And our chemistry friends can do real magic with these benzene rings and can get you any amount of properties and materials with them. But so this, for example, this aluminum quinoline AlQ3, you can see this is LQ3 or just benzene rings. Okay, this is pentacene, 5 of them. Okay, so these are small molecules. And how do they pack? They pack just like cornflakes. Okay, there is no bonding between. Okay, but these can also make crystals. So instead of silicon or carbon forming, very hard bonds, these are simply van der Waals solids packed together. So this is like cornflakes. Okay, and what Richard Friend found, that similar properties can be found with carbon-based chains, which are like noodles. Okay, chain with short branches or chain with long branches. So these branch polymers are a lot more flexible. So the soft electronics, these are the two kinds of materials which form the basis of really soft electronics. Okay, so we have everything in inorganic electronics. Of course, it's very mature, but correspondingly, these all the products that you will see with organic electronics at our center. Okay, light emitting diode display, solar cell, they are all made at our center. Of course, there are transistors and all kinds of sensors. So this is a technology motivated by electronics for everybody, for everywhere. All right, and I'll illustrate that as I go along. Okay, so what are the typical components of flexible electronics? I've said organic light emitting diode. It is much more easier to make them than conventional semiconductor electronics. Why is that? It's just deposit them, okay, very inexpensive processes, and let's say between anode and cathode, which can be a glass substrate, and you get an organic light emitting diode. Or a thin film, have its organic semiconductor as a thin film, and then deposit source and drain and a gate, and you get an organic thin film transistor. Okay, or one of these diodes properly heterostructures, we can make organic solar cell. Okay, or an organic memory device. Okay, and we have a patent for white lights, an organic light emitting diode with a single layer, which you can make a white light emitting diode instead of having 3 different OLEDs. Okay, just a single layer. If it's properly suited, if the physics is done, then you can get light emitting diodes, for which actually we have a patent. So these are the typical. So these are playing a huge role in many grand challenges currently: energy, health, environment, and education. And so the display is being flexible. So there is large and they're flexible. Okay, organic photovoltaics or flexible batteries. Okay, or a robotic skin. A robot has a skin which is like human skin. So this is basically a skin with lots of thin film transistors coated with it. Or packaging, smart packaging, which can figure out whether the fruit is fresh or not. And of course, IoT or printed polymer RFIDs. So these are, each one of them have taken off in a big way, and they're maturing to come to the market soon. So this is the new age of what I call a macro electronics. You can see that there are all the components you have to have: displays, thin film electronics, solar cells, lighting, RFID sensors, and Internet of Things tags. All right. But the difference is that now it has to be printable, flexible, large, disposable, and cost effective. That is soft electronics. Okay. And that is macro electronics as opposed to microelectronics. So small molecules can be deposited in systems like this, which you have in the lab, which are something like our traditional semiconductor and pretty high equipment. But what is more important, that you can actually just do solution processing. Okay, for example, in this, I'm showing that for functionality, you can use quantum dots. Okay, let's say cadmium selenide. And for processing, you can use polymer. And you can simply do solution processing and and you can make different dia of cadmium selenide in the solution and make LEDs out of that, as we normally make. Okay, so different colors, different functionality, but it is all done on plastic with a simple solution processing, and hence it can be large area, it will be soft, it will be cost effective. Okay, so what you are basically doing, you are nano engineering, okay, to produce macro electronics. You can pack and align, okay, these molecules, or you can simply blend, or you can embed carbon nanotubes or a PCBM, which is like C60 attached. Why can you do that? Because for better luminescence, higher mobility of carriers, stability of devices, but this is not electronics. Okay, you can call them excitonics. The reason is these are like actually insulators. Okay, but and hence when you create an electron and hole, it becomes an exciton. So it is the physics is very different. So you get the similar material, but the physics of how each of these work is very different from the traditional transistor or a traditional diode. I will have more to say about this as I go along with it. So the key use in flexible electronics is what we call a ink development, is a key use of nano, okay, in flexible. So how do you make, for example, a gold or silver on plastic? Because so you have to go at the nanoscale to be able to make them, or soluble CNT. So you have to make everything soluble so that you can do processing. So what we do is, for example, gold. Let's take gold. We take gold and make gold nanoparticles, but decorate with organic molecules. All right, such that So the question is, okay. So why is it taking time? So how do you? The question is, how do you print metals on plastic or paper? Okay, so gold is melting point is 1064 degrees Celsius, and that is why we use vacuum to actually sublimate it. All right. So, but how do you make solution processing? Once you go to a size of 1 to 2 nanometers, the melting point, or let's say sintering point, can come down as low as 153 degrees Celsius. All right. So melting of gold you can do, and silver, in fact, we do at about 123 or 130 degrees Celsius. And then you can actually put it on plastic or paper. Just to show you, okay, so there is we work out the physics of this. These are gold nanoparticles, and then so they are unstable if they're alone. But once decorated, okay, with small molecules, they are stable. And when I want them to become gold, what I do is I let them give some energy or some process, especially heating. That heating is very low, okay, just to break this bond. Once these bonds vibrate and break, they join up, finally forming the bulk gold. So you use nanoparticles, okay, to form bulk gold, and this temperature required is only 153 degree Celsius. Okay, that's key. So similarly, we make conductive silver. In fact, we have make a conductive silver pen, and we have started a company which does such that it can be used in education and hobby making in schools. All right, that is, you can make circuits on your paper and normal paper. Okay, and lots of educational kits. In fact, we are trying to market it as a company, as a startup company. Okay, with educational kits along with just a simple notebook. You don't require soldering iron to solder. Okay, or we can print conductive silver, let's say huge cloths. Let's say what is required. For example, this can be let you have pockets in which it is you cannot do theft, electronic theft, if you have your passport or your credit cards inside cloth which is coated with silicon. All right. So we make many inks like that: silver ink, copper ink. That is, we normally, in fact, we're trying to as a major project replace silver with copper, because copper is a lot more less effective, except that copper gets oxidized very quickly. So we have a new patent on how to deposit through solution processing copper on plastic, and you can print like newspaper. All right. So ink formation, we do that. So all kinds of. So the question is now, inks are used to make different kinds of functionality, whether it's polymer or dielectric, or, for example, this is a conductive cloth. Okay, so a cloth which is, and as I told you, this application of EMI shielding, which is for card protection and information protection. All right. So we have OLED. Let me go to a device which is lighting and signage and display. I'll show you a quick examples of what we What is an organic light emitting diode? Organic light emitting diode is a cathode and an anode, that it is sandwiched between cathode and anode organic layers, multiple organic layers which are just nanometer thick, okay, on a substrate. And then we just attach. So you inject holes into one side, electrons on one side, and they form an exciton, and this exciton gives you light. All right, just a minute. Sorry. Okay, sorry. So that gives you light. Okay, and this is a simple principle, and this is what actually both Friend and Chang had discovered in discovering organic light emitting diode. What is important is these organic layers are few nanometers thick only. All right. So we have, for example, automated system, which are 3 robots which can make you OLEDs, which are that's organic chambers. Okay. And you have this is a glove box, for example. You can introduce here the glass substrate and then deposit a red LED and a blue LED and a green LED, and that can make a display. Okay. This is the team which goes into making. So we have a cluster tool. This tool, we designed it and got it made in Korea, okay, because still the level of automation in India was not good enough. Probably now we can make it ourselves. So this will give rise to lighting, okay. For example, flexible panels, okay. So these lighting panels, or where it can be used architecturally, okay. So this is of course LG's one. This is not ours one, but we have now flexible. I'm just giving you such that a feel for the kind of applications that is required. So we get in rigid glass, but you can make it unflexible. Now we can print them. All right, and these are simply nice diodes. Okay, where these are diodes made at our center, which are quite bright and colors can be changed. Okay, I'm just giving you a quick round of applications. For example, these are printed 7-segment displays. All right. So in fact, auto industry want us to print lots of things for the inside the auto as flexible, which can be disposed later, but it should be flexible such that fittings are embedded in the plastic itself. So in fact, it's giving rise to embedded electronics as a discipline by itself. So we have a dot matrix display. Okay. So and then we have shown them as demonstrators for industry to get interested. So there is, for example, here, okay, there is a small dot matrix display which is made on plastic and at our center. All right. So signage is one of the major applications for the tail light or auto for the auto inside. So this was the first passive matrix OLED display that we had made, which is to industry standard. All right. So the idea is that later you can have flexible photographs also getting printed like that. All right. So this, you can have a panel which is really flexible. This is, of course, Samsung. Samsung has taken a major lead in this technology. Now let me come to a case study where I can demonstrate a little bit of physics. Okay, this is an old work of ours, but this will give you a feel at even an undergraduate level. This is we have also PN junction, okay, but the way the PN junction works is very different. So I'm giving an example. This is a homo junction, meaning it is not a P-type, N-type junction, but a similar N-type material. So this is what? This is a just benzene rings, okay. This is a compound, and in which you can put another compound. Don't worry about the nature of the or names of the compounds, but we just sandwich between, let's say, an aluminum cathode and a glass substrate, and glass substrate has an ITO anode, and then inside that, okay, we put layers which is like 150 nanometers or even 10 to 100 nanometers. Okay, so a layer which is doped and which is layer which is not doped. Okay, so that is itself gives a homojunction. So intrinsic layer, okay, and a p-doped layer. And then you can make, and then why is it important? It is, you can see the PN junction, okay, this is, remember the current density changes from 10 to the power minus 10 to 10 to the power minus 2, 8 orders of magnitude. All right, so the leakage current is so low that it is very difficult to even measure. Okay, and there's 8 orders of shooting up. Okay, similar thing happens in PN junction, but important thing is the physics is very different. Okay, why? Because in normal junction, if you have studied it, this will be temperature dependent. The slope, the way it is going is QV by KBT. In this case, you can see the slope from even from 175K to 300K is exactly the same. So it's not the same physics, though it is going up exponentially. So it's like a diode, but the physics is very different. All right. The physics is simply J naught. There is no temperature here. Okay. So simply something, a xi parameter into a voltage. All right. And so why is that? I'll just give a simple model. This is a phenomenological model. So you have the intrinsic layer here, the doped layer here, okay, and there is a density of states of energy, okay, they are mismatched, okay, because of the doping. All right, so what you do is once you apply voltage, then the energy levels on the inner side you can start changing where it's, okay, if you some threshold, then the electrons can come to this side. So this process is not because of a overcoming a barrier, but tunneling, and that is why it is temperature independent. And I'm sure you have studied that the tunneling process is not temperature dependent, and hence it is just an example to show that the similar sounding devices, okay, in organic and inorganic, but they would be very different in their actual functioning. And that is the kind of physics that we normally investigate. For example, here we figured out that a little bit of physics that it depends upon the density of states, which is a Gaussian. Okay, if you have done solid state physics for normal 3D solids, the density of states is parabolic. Okay, that is e to the power half. But here in these amorphous solids, it is because of the random distribution, the density of states is Gaussian, and this Gaussian property we can obtain from the J itself. Okay, so and we can work out from our physics what is the density of states of the energy. So it's a very simple physics of JV characteristics. Okay, and from the threshold we can make out what is the broadening parameter which is of the Gaussian density of states. I just wanted to give you that how important is simple experiments. That is IV done for different temperatures, okay? And you can get a very rich physics, which is very different from traditional semiconductor devices that you get in silicon or germanium or gallium arsenide, all right? Let me give you a little bit of printing. That is what finally is important on paper, plastic, and cord. So the whole idea is to be able to make these devices not in one or two, but large area. So in 2015 we started. So we started printability starting. Now we have industrial compatible sheet to sheet printing. That is, you can take A4 sheets, you can print A4 sheets. And we have also have what is called roll to roll here, like, okay. So like cloth, we can do that. So why is it important? Only if you do this, such large area, you can produce a low production cost. So it should be as low as newspaper or less than that. Okay, and that is you have to have you must be printing crores of them because of roll-to-roll processes. While in traditional microelectronics is done by miniaturizing. You are billions of transistors in a microprocessor by miniaturizing on a 12-inch silicon wafer. But here, roll miles and miles of printing to produce billions of devices. That is the roadmap. So we have for sheet-to-sheet printing, I will not go into the details, all kinds. So if you name a printing method in normal traditional printing, and we have it in our center, okay, including you can say inkjet printing, all right, and inkjet, all kinds of screen printing, the slot die coating. So all kinds of printing, we can do both sheet to sheet and roll to roll. Let me show you large area inkjet printing. This is a tabletop. Okay, so you can do with 512 nozzle. Now we have for 2 into 1 to about 24 nozzles for roll to roll printing, and then you can combine them to at the same time multiple print heads. Okay, to print, let's say, a line like that at one go. Okay, I'll show you that. Okay, so this large area printing. So you can see this is a printing machine that we have designed and got it made in England. And so this is, it can roll 50 meters per minute. Okay, from 10 meters per minute, which you normally do, it can go to 15 meters per minute wide. Okay, so and substrate width can be 10 centimeter to 30 centimeter. So you unwind, clean, and there are one printing. So here it can do any kind of printing. This is modular. Okay, so you can do inkjet printing, you can do screen printing, you can just put in any printer that you want. So similarly, another stage. After printing, what is important physics lies in how do you sinter to get the functionality. Here it is only deposition. But if you want semiconductor or metal functionality, you have to do lots of sintering mechanisms. So that all the mechanisms are lined up here. Okay. Similarly, you print another layer and all of them are lined up here. And then you laminate and you can do another more layer. So this is the, for example, R2R line, which is like 20 meters. Okay. This whole, in our center, we have, this is like 20 meters. Okay. The whole machine. Okay. This is a printing station. Okay. So let me show you, for example, we have designed a jacket which can be heated, and we give it to our security personnel here in December in Kanpur to wear it with a heater in the jacket. So that heater is made with this. Okay. And we're trying to commercialize that. So take the substrate, which is plastic. So unwind, clean it with plasma. There's a plasma cleaner here. All right. And then print. In this case, we are printing it with screen printing. All right. So we have a screen printer and the, okay. So, and then you dry it. So the physics lies in actually understanding how to convert a deposited layer to the functional. Okay. And this physics is very, very interesting physics. And then you can print another layer on top. Okay. So register pads. So that was metal, silver metal, and then the register pads. All right. And then again drying. And then finally you get these register pads, which you can now insert into the jacket and provide the current from a battery pack that you carry, just like your mobile battery pack. Okay. And it keeps you warm. The material chosen is such that there is no danger. There is no electronics. It is just simply that it is beyond a certain temperature, it simply folds back. Okay. Such that there is no electronics to control. It is just pure resistor. Okay. But it is done in roll to roll process. Let me come to thin film transistor. Okay. And we have done a lot of work in the physics of this, but let me tell you why. So this is the PET substrate, and we have the whole process can be done by inkjet printing. Okay, so this is metal and then inkjet printed oxide, PVPH, a particular polymer, and then on top we put a pentacene, but now solution process. It's called TIPS pentacene. Okay, so if you look at optically, then it will look like this. This is the gate and the source, and in between TIPS pentacene, which is like this. So with that, we can make several layers. So the color that you see is because of TIPS pentacene. All right. So you can make this. So here it is a 6 printed transistors on a single plastic substrate. Though it's a transistor, the physics of this transistor is thin film transistor, very different from amorphous silicon transistor or silicon transistor. So we have spent most of our time actually studying that physics. Let me go to organic solar cells, which you can probably understand. So Higa, who got Nobel Prize in 2007, wanted the solar cells to be made like this. That was 2007. Okay, and that was the dream. And the idea was to be able to print it like plastic substrate in solar cells with the functional inks, such that now you can get just like print it like newspaper. It's close to reality now. Okay, to make solar cells which are now rollable, except that it is only 6 to 7%. Now a German company is doing it for 10%, but the area is so large, this 10% is all right for many applications. All right. So let me give you a little bit of one example of the physics. So this is a simple diode. Okay. This is simply ITO, aluminum, and what is this a compound P3H3, in which we have put this C60 molecules, okay, to make it light sensitive. So now you can see if you put light on, the current density changes the reverse current
Uh,
density.
Professor,
Yeah,
may I interrupt you?
yeah,
Probably
sure.
you are not on the slide you are mentioning. It's a printing
Oh,
of plastic electronics you are presenting right now. Are you referring
why
to
is
this
that? I
slide
see.
or
Oh, it is taking time probably. Okay. A plastic
this slide is printing of plastic electronics? Are you referring to this slide or something else?
electron. Okay, now you are seeing JV characteristics.
Not. Yes, yes, it's there. It's there.
Yeah. Okay. So I
Okay.
think suddenly the internet is slower probably. All right. Sorry, I was going at great speed probably. Okay. So this is a device which is aluminum P3H3. How much time I have now? Uh, oh, I see. Okay. So I have another 5, 7 minutes, right? Uh, uh,
Yes, yes, you can go ahead for 6, 7 minutes.
okay. So and that's why I was trying to hurry up. Okay. So ITO and the layer and aluminum. So now put light on and you can see that it's all tend to uh, and hence it is delivering power. Okay, this is photosensitive, but if it is in the third quadrant, then it derives power. Now, what is not understood is what are the mechanisms of degradation is a major challenge for this. So you are trying to understand that. So in fact, this VOC open circuit voltage decay measurement that was with silicon. Okay, so similar measurement now we do with is open circuit. That is, take the solar cell. Okay, and that tells you the how the what are the recombination processes or the defect processes that is making you inefficient. Okay, so it's a very simple measurement. So you can see VOC, and now you can see the time is in log scale. Okay, and some of us having studied in bits with a solid electronics background, actually we could figure out that a lot of people are doing mistake in not doing proper electronics in getting VOC. And once we do that, okay, you can see that this is with proper buffer. Simple thing is like that. This is undergraduate stuff. Okay, if you do a proper buffer, then you can get a log scale straight line over many orders of magnitude from 10 microns to 10 to hours. All right, and so this was not explained. Why is it not exponentially decaying but decaying as log time? The open circuit voltage, okay, how does it decay with in log time? Okay, so very straight lines, and it's not very temperature sensitive. All right, and then we one of my students could figure that. Oh, sorry. Okay, are you seeing now the proper this thing? Okay, so we figured out that this is nothing but that if you take a capacitor and a diode in combination, which is like really undergraduate physics, okay, then you can recreate exactly this, and from that you can derive many mm, the important parameters which was difficult to do by very sophisticated instruments. All right, so the physics is extremely interesting. So for lack of time I will not describe it further, but I would like you to see that this is a phenomena which is from 100 nanoseconds to this is 100 minutes, okay, to this is 10 to the power or 1000, okay, is all right. Now, let me come towards the end of the lecture, having given you two examples of the, just to show that the physics is very different. But why, what kind of devices we like to do, and why is this an explosive revolution? Is because the principal applications of any sufficiently, this is Herbert Kromer, who got Nobel Prize. He says that, I call it a Kromer's theorem. Okay, are sufficiently new and innovative technology always have been and will continue to be applications created by technology. So currently we have all the physics, okay, but to be able to make new devices, okay, with this technology such that it goes to the market, that is what is actually people are being creative about. So there is a huge amount of creative power being used to produce new. It is not just to say that what was done with silicon, we can do with this. No, we should be able to do devices which are for new applications. Kromer's theorem 2, ultimately progress in applications is not deterministic, but opportunistic. So many devices we have done, but being applied physicists, okay, sometimes we get very excited about certain things that we have done, but market doesn't take it. Okay, that's because it is not deterministic. So that is why in all my physics projects, we actually involve industry such that their input is important to be able to become opportunistic and do only those applications which has a possibility of hitting the market. Okay, and that is why we have now put this center, which is okay. Now quickly over next 2-3 minutes, I will say what are the main challenges in physics in making this electronics flexible. One is it is all low temperature processing. Is paper, plastic, paper, plastic, or textile. So developing functional inks, functional meaning semiconductors, metals, everything we have to print and sinter, okay, less than 150 degrees Celsius because it is substrate is paper or plastic. Or now people are making steel which is flexible, okay, or glass on which you can print which is flexible. Okay, so these are high temperature substrate but flexible. So there are two. So this is a major challenge to be able to make either low temperature substrates or high temperature substrates. Challenge 2 is the physics changes as you bend. All right. So the color might change if you bend. So electronic properties and mechanical properties and both properties and life of the devices are interconnected. Okay, and they must be wearable. I should be able to wash them. Okay, or a lot of wearable electronics today is from the study of the sensor of the sweat. All right, so that is the challenge 2. Challenge 3 is lots of functionality you get, but you have to encapsulate it. Since you make these devices with so much less energy, they can also degrade very fast, especially with oxygen and moisture. So study of encapsulation and degradation has become one of the major challenges, which leads to materials design and even sealing and multi-layers. These are all highly physics-oriented projects to be able to do this. Challenge 4 is, of course, printing technology, large area such that it must be cost-effective. People are trying to make large area with vacuum processing. Some companies are trying to do that, and we are trying to do it also solution processing, the kind that I showed you. All right. So for applied physicists like me, the most important is called the valley of death. That is research resources and actual commercialization. Normally, most of us fall in here. And in this technology, we are somewhere here. All right. So a lot of research has gone in, and now commercialization is beginning to start. And that is why we are beginning to have a lot of startup companies, so such that you can do market penetration. I am probably out of time. So, but this is something that we show, products of the future. This is something we say, okay, that we will have a computer which is like pen-like, and if once you take it out, and you can take your computer out of this. All right. So let me end because it was only for 40 minutes. So I must have spoken very fast. So let me acknowledge my we call it the Flexi team, my flexible electronics team, my students, and of course, Ministry of Information Technology and Government of India. With that, let me thank you all for listening. I can take some questions if you have time.
Okay, thanks a lot, Professor Mohapatra. We can take few questions. So if you have any
Yeah,
question, please.
I hope I am in time. I was trying to pack in a lot of it in
Yeah,
in
I
that
know.
time.
Yeah. It's
Yeah,
very difficult to,
yeah,
but
all right.
yeah. So we can take a few questions. So if you have any question, please raise your hand, and then I will come to you, and you can ask your question.
Yeah, so I've stopped presenting so I can interact. Yes, any questions? I don't know if any
Yeah,
of you in the,
Professor Manjula Devi.
yeah.
Yes, you may ask, Professor Manjula Devi.
Yeah, sir, what kind of OLED devices have been already achieved through your center?
Oh, we make both. See, at the moment we do also vacuum, okay, but our main emphasis currently at the moment so that you can print them. Okay, so both polymer we make red, green, blue, and flexible. Okay, so and we are also studying new materials which can be commercialized for OLED companies. Okay, so I showed some examples of them, different materials. A particular OLED has almost seven different kinds of materials to be stacked, each few nanometers, and with precise properties.
No,
Okay,
my question was like, is there any device level application
yeah,
has
yeah,
been?
I showed you some of them. Okay, so we have those flexible dot matrix displays. Okay, and for embedded electronics inside auto and lighting. Okay, we have also the
So is that
lighting
being
devices
gone
which
into the commercial level, sir? So my question was like,
no commercialization. We don't do commercialization. We are starting company. We handhold companies to do it. Yeah.
okay. So because I work on actually liquid crystal materials which are useful for display, so that's the question I had. Like,
Oh, I
oh,
see. Okay, yeah, liquid crystal materials. Okay, yeah. We have a
it's a
project.
very good talk, sir. So I just wanted to. That's why I was seeing like how
Okay,
because
sure.
it's hard to go onto the industrial level applications. So
Yeah, right. In fact, in this country, we don't have proper liquid crystal. In one project of ISRO, we wanted a layer of liquid crystal, and nobody could make it. So we are also now trying to make that also. Okay, it's for a defense project, which is antenna, in which we are also making liquid crystal, but that's not our main aim. Yeah, go ahead.
yeah, thank
Anybody
you.
else? Any basic
Yes,
question also?
Professor
Yeah, yeah,
Devashish.
yeah,
Professor
sir.
Devashish.
Sir,
Yes,
Devashish here.
Devashish. Yeah,
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 how are you, sir? Yeah,
ah,
fantastic talk,
fine.
sir. Fantastic talk. So I
Yeah,
know you very well, and I'm not surprised that we achieved this thing. Sir,
yeah,
my
yeah.
question is not my question
Okay,
is not related to the physics or technology or whatever you have done. So
yeah,
the basic question is, so whatever you have done,
yeah.
based on that, what is our position in the world technology, in, technology?
All right.
So
Let me tell you, there are two kinds of things.
what is our
Uh,
basically what
so
is our future?
Right. So once the basic, I think the small molecule thing is now become extremely commercial. So Samsung and LGs, they can put
Yeah,
billions of dollars to get them, right? You have now
yeah.
OLEDs. So we don't do that. Okay. We do, which are lot more mass manufacturing for Indian context or even any populous country. All right. So printing
Okay.
is yet to be done, which is to be commercialized. All right. So
Right.
with small molecules display is extremely commercial. In fact, now you have an Samsung display, which is Samsung LED, which is marketed just this month, which is rollable. Okay, on your
Yeah,
desk, it
yeah,
will
yeah.
come up when you want to see it. There's already advertisements are coming in. So that has become extremely commercial. So we don't want to get into there. Of course, once they put billions of dollars into it. So we are more into IoT, the sensors, the biosensors, and large area displays, which are which can be used for in the Indian context a lot more. All right.
Okay.
So there is a huge future in that.
Yeah. Yeah.
Yeah. So in near future, can we beat China? That is the main
I
challenge.
yeah, that we don't want to yeah, I don't think we are in that kind of race, but yes, at least some hardware projects. For
Yes.
example, one of our projects is taking a lot of commercial of anti-counterfeiting, which is a few paisa on every packet. Okay, now soon we'll have our labels for finding out anti-counterfeiting. Okay,
Okay. Okay.
so which is only few paisa. That a technology which lots of commercial companies are taking.
Okay.
Okay,
Okay. Great. Great.
and so that is already a mature technology from our center. All right.
So where is your center, sir? Is it in central building in IIT Kanpur or
Sample
where?
building was too small, so there we do now research. And for
Okay.
industrial thing, we have made a six-floor building in behind ACMS. Okay.
Behind ACMS. Okay.
Yeah.
I didn't visit for a long
Yeah,
time.
yeah. We have a, six-floor huge building with about
Okay.
120 people working there.
Oh my God. Oh, great.
Okay.
Great. I must visit that place.
Yeah,
Okay.
sure. All of you are welcome. Yeah.
Yeah. Yeah. Thank you, sir. Thank you. Thank you. So that's all from my side, Rakesh.
Yeah.
Yeah, Divya Dixit.
Yes, sir. Good evening, sir. I'm a first year student here at BITS Pilani. Sir, I had a
First year of
question.
UG.
Yes, sir. I just
Oh, I see.
joined one
Good.
month
So,
ago, and
yeah,
I saw the
good.
talk on flexible technology, and I'm rather interested. I
Yeah,
became
good that I
interested to
kept it.
those
Yeah,
LG
yeah,
and Samsung things you showed earlier, so I was a bit interested in that technology already. Sir, I had a question. So we have seen display technology involving flexible already, like you showed
yes,
some of it
yes, yeah.
and some lighting
Uh,
also. Sir,
yeah.
can processing also take place on flexible surfaces also? Like, can we, let's say, have a cloth which is sort of processing things,
Yeah,
and
yeah. We are trying to make plastic chips.
which
For
are
example,
flexible?
hundreds of transistors on plastic and in meters.
And then can we stack them on top of another? Because like currently we have solid processors only. So flexible
No, no,
processors.
no, no, no. We are only solution processing. Okay. So inject, you inject, print the whole circuit.
Okay.
All right. All layers, everything. What it comes out is a fully made circuit.
Okay, sir. Got it.
That is what roll to roll processing was there. Maybe I was too fast. Yeah.
Okay, sir.
Yeah.
Got it.
Okay.
Okay, Sweta Mishra.
Yeah.
Good evening, sir.
Yes.
So it was a nice presentation. Actually, I don't know whether I missed it or I wanted to ask, what are the limitations on the material? Are there any limitations on the material that we are, like you mentioned about anti-counterfeiting? So there are now upconverting materials like NaF4 doped with various rare earths, and they have a different shape morphology as you do the
Yeah. So that
semiconductor.
is, yeah. But
So
for us, it has to be electronics. All right.
yeah.
So, yeah, complete your question.
So I just wanted to ask, like, are these also like, if they means, is this only the thing that small molecule, small spherical kind of particles only can be processed, or there is a variety of molecules can be used in
So
this?
see, our chemistry friends are actually magicians. Okay.
Okay.
So in inorganic semiconductors, we had only silicon, gallium arsenide, germanium, and a few. In organic semiconductors, you have millions. Okay, there is actually is a plenty. So the question is how to choose it such that the processing can be done well.
Yeah.
That is the major challenge. So we are actually, for example, we are making our own inks. We are trying to make our own semiconductors. So material challenge is at the root of it. The limitation is that how to be able to make it processable and yet make it functional, which does not degrade. All
Yeah.
right.
So that's what the
That
question
that
actually.
is that is the major challenge. That is why
Okay.
we physicists are involved. Okay.
Okay. Yeah. Thank you, sir.
Okay, we may take one more question if
Yeah.
anybody has.
Yes. Any question?
Yeah, Professor KG Krishna.
Yeah, hello, sir.
Yeah.
Yeah. This actually, your talk is very exciting about the future opportunities.
Yes.
My memory goes back to my days when a blue LED was announced, and that
Correct.
changed the whole industry today, LED lighting.
Yeah,
Okay.
and got a Nobel Prize. Yeah.
Yeah, exactly. And for a long time. For a long time.
Gallium nitride. Yeah.
Yes. And today, I think these flexible displays have already been commercialized, and we are seeing in
Correct.
terms of mobile phones and rollable
Correct.
TVs.
Correct.
But I heard one other technology, sir, because I'm not a physicist, but that is called bioluminescence. What way is it that the way, for example, the fireflies emit light?
Yeah. So that is
Yeah.
for some tags, people are trying that. Okay.
Okay.
For inexpensive, in where a sensor can display a color. Okay. So bioluminescence is being studied in great length. Okay.
Yeah.
Is actually a lot of organic chemistry and physics of luminescence is involved there.
Yeah.
We are trying to make sensors also with display, but from the inorganic side, not with the bio. But we have biosensors. We are working on biosensors. All right.
Yeah.
And we have lots of sensors for health devices is one of our major programs. Okay.
Yeah.
For example, breast cancer, we have a major program. Yeah.
Yeah. Yeah. That. Yeah. So what you are saying is that is another area of technology.
Yes.
Biological.
Anything that can make things
processes.
flexible. People want people want electronics now not to be in a box. They want to be on their cloth, on their wrist. Okay. So on their handkerchief. Okay. So not on in a box to which you connect a wire. No more. And in the new age of electronics, every object has to become intelligent. So there will be a tag. So just like a label, so every object will have a tag which is through internet in the Internet of Things. So that is also a major aim. Yeah.
Okay. Thank you, sir.
Okay.
Okay,
Anybody
so
else?
I think there will be no more question. I would like to thank Professor Y.N. Mohapatra for this excellent talk. And I know it was very difficult for you to present so many things
Yeah, right.
in a
I
limited
was
time.
doing it a little high speed. Yeah.
Yeah. So I think we would be very happy to receive you in Pilani when situation improves.
Yeah, right.
And you may stay for a week and you can give a series of talks on this.
Would love
So
to.
that-
Yeah.
so that we can learn a lot of things from you.
Yeah.
And it was in fact, a great talk on this soft and flexible electronics and its marketability. So, on behalf of the physics department, I'm again thankful to you for accepting this talk. And I remember that you instantaneously
I saw
wrote to
Bits
me
Pilani.
replied to me that you want to give a talk because it's a bit Pilani.
Yes.
And I hope you might be having a lot of memories of Bits Pilani. So
Absolutely. And Pilani must have changed a lot. Okay. We keep talking about
so,
it.
Yeah, so we would be happy to welcome you. So if situation improves, in that case,
Yes.
you are welcome to visit our department and your alma mater. And
Yes.
can-
Absolutely.
Yeah.
Okay. Thank you.
So with
Thank you,
this,
Professor.
I thank all the people who attended this talk, and also Professor Mohapatra.
Thank you. It's my pleasure.
Yeah. So with this note, I formally close this talk.
Thank you.
Thank you very much.
Thank you.
Thank you, sir.